Hello, my name is Yusra Al-Qabbani, and I am an associate professor at Halmstad University. Today, I will present to you the journey of Halmstad University researchers and their efforts to make computers run faster. Just to justify why we want always our computers to run faster, I want you to look at this graph that shows the different generations of mobile networks and how they speed up with every generation. And you can see that, for example, 5G is almost 100 times faster than 4G, and so on. So we are increasing the speed 2 orders of magnitude with every generation. And we need our computers and devices to respond fast and cope with this increase in the speed. If we check just simply running a computer on a single processor, we can see from this curve that recently, starting the 2010s, the speed up of one processor core is stagnating. So we cannot really achieve high speeds with one single core anymore. So we need to switch to parallelism. So instead of doing one task using one processor, you now use multiple processors or multiple cores to execute the same task. And this is how you speed up things. So let me show you a small example here. We have a very simple program made of 5 lines. We are just adding, subtracting, and multiplying numbers. But then basically, you can represent this program as a graph, as shown in this figure. This graph basically represents the computations you want to do in circles, so the addition, the subtraction, the multiplication. And then your data will flow from the top of the graph to the bottom till you compute everything in the computer program. And this is why this graph is called a data flow graph, because it represents how the data flows through the computations. And the nice thing about this graph is that, first of all, it shows which computations in your program are dependent on the others and which are independent. And as we can see here, the addition, subtraction, and the third addition are independent on each other, which means we can do them in parallel. Whereas the multiplication operations depend on the results from the addition and subtraction, so we cannot execute them at the beginning. We have to wait till we first compute the first step and then go to the second step of multiplication. But if you have many processing cores collaborating to execute this program, instead of executing this program in step by step, so taking 5 steps, now you can finish the program in 2 steps. And this is basically speeding up the program without having to have faster processors. Now, typically, new trends in parallel computing started by having many processing cores in the same chip. So usually we have identical cores that are connected in a network. And now the problem would be, how can you map your program to run as fast as possible in this system, which we call a homogeneous many-core system. And the reason we call it homogeneous is that basically it has the identical cores. So there is no difference between one core and the other. And here in Halmstad, in 2014, we managed to develop tools that takes a program in a representation similar to the data flow graph I showed you. This representation is called CAL. So CAL is a programming language that takes program represented in data flow format and convert this into a program that runs in parallel on a many-core system. And this is why we call the tool CAL to many. But then can we do better? Can we make our system even run faster? And the answer is yes. But to make the system run faster, you need to go from the general purpose solution that we presented and start looking at the application and become more specific towards the application. So now we can look at the application again we have, which is this simple example. And we can see that usually in computing, multiplication is much slower than addition and subtraction. So usually, step 1 here in this program will take much longer time. I always confuse things, but will take much smaller time than step 2. So we can make our program faster by trying to make those multipliers faster. Of course, this means that we'll have to pay more money and get better circuits. And those circuits will be also consuming more energy, which is something you don't want to do unnecessarily. But if you look at this application, it seems that you only need 2 multipliers. You don't need to add a very fast multiplier to every core in your system. So basically, you start adding very expensive circuits, but very few of them to your system. And this will cause your application to be faster. So to show you an example of how this is done, here is a picture of a GPU or a graphics processing unit. We all use graphics processing units in our computers, especially if you like gaming. And GPUs are massively parallel circuits. Without understanding anything about the hardware, if you look at the diagram here, we can see repetitive green blocks. So this represents the parallelism. If we look closer to those repetitive blocks, let me come this way, we can see that there are actually blocks that don't look the same. And this means that this architecture is not homogeneous, it's more heterogeneous, because we have now specialized blocks that will speed up some operations related to graphics. For example, this big yellow block is actually called a ray tracing core, which focuses on ray tracing, which is very important for graphics. So the question now we are trying to handle, can we actually do that automatically without really manually studying the application and figuring out which operations need to be faster? And the answer is yes. So in 2018, we took our cal2many tool, which we talked about before, and we tried to modify it to generate what we call domain-specific heterogeneous solutions, where basically, after mapping our application to run in parallel on a homogeneous system, what we do is we try to automatically profile our program and look where the program spends most of the time. If these computations can be sped up, the program can be much faster. So what we do is we extract those parts that are computationally intensive, we convert them into hardware, creating accelerators, and connect those accelerators not to every core in the system, but to some of the cores, because you don't need to pay for extra hardware that you don't need, and you don't want to pay for the extra power consumption. And basically, you have what we call a heterogeneous system, but it is actually still flexible in the sense that you still can map any application to it. However, it is optimized and it will perform best for this set of applications that we studied and added accelerators for. So for our applications, the new system with 2 multipliers will work for any application, but will work best for applications that look like our application, that needs those 2 fast multipliers. So basically, it's a great idea that can tailor the architecture, and the architecture now becomes domain-specific since it handles a domain of applications. Can we do better? The answer is yes, actually. Do we really need all those cores? The answer is no. Usually, if you have a specific application and you want to focus on this application, you can actually tailor fit your hardware architecture to fit this graph. So you just need 2 adders, 1 subtractor, 2 multipliers, and that's it. You don't need really all those cores. So we can actually generate a circuit that looks exactly like our algorithm and make it run fast, at the expense that this circuit is now inflexible. You cannot use it to run other applications. So this becomes an application-specific architecture. And basically, in 2021, we started researching that in Halmstad University, where we have tools that would automatically take your application. And here we were focusing on machine learning applications. So we take a machine learning-based application, and we convert the whole application into hardware. And this should give you the best performance. However, now we are easing it because you don't need to be a hardware expert to have a hardware circuit running the machine learning application. Instead, we start from regular software where you design your machine learning application normally, and then our tool would automatically convert it to fast and efficient hardware. Well, can we do better? And the answer is yes. The main reason we cannot speed up our current processors is that basically all processors now are manufactured with CMOS technology, and CMOS technology is hitting a power and memory wall. So we cannot get them faster. Can we use other technologies to make faster things? And the answer is yes. And this research was done in collaboration with researchers in the George Washington University, where we tried to implement a CAM, or a content associative memory. And associative memory basically is a piece of hardware that you ask, do you have this data stored in you? And it will answer, no, we don't have this data, or yes, we have this data in this specific location. So it looks like a search engine. And doing this search engine in CMOS technology is inefficient, especially if the memory size is large, and it consumes a lot of power, so it's impractical. So now we try to replace the search engine with an optical search engine, so searching in parallel using the speed of light. However, we kept the interfaces electrical. So you can plug it into a regular electrical circuit with no problem. And there we achieved actually 2 orders of magnitude faster circuits. So, and the side effect that is very nice, we also reduced the power consumption to 3 orders of magnitude. So 1,000 times less power consumption. So just to summarize, we started our solutions from a very general solution that works for any application. And this was completely software solution. We have a platform with many cores, and then we basically run the application on those many cores. Then we started moving towards hardware solutions. So we partially modify the hardware in the standard platform by adding accelerators, and we get domain-specific architectures. Then we move to the total hardware solution, which is the very specific solution to a single application. Of course, at every stage of this, we have many possible solutions for each problem, but you need to trade off many factors, including cost, how much money you want to pay for this, energy and power consumption, reliability, and security. So it's a multi-factor optimization problem that we need to work hard on in order to provide the best platforms for our applications and get the fastest response. That's it. Thank you very much.
Thank you so much, Yosra, for a fascinating and fantastic presentation. And here you are.
Thank you very much for giving me the opportunity.
Well, it was great. Well, you know, I'm from another area, so I don't understand it all, but I have some questions for you.
Okay.
So, well, first of all, today we're in Halmstad, and I'm just curious, how did you end up in Halmstad?
Well, I was working in George Washington University in DC, and I saw an ad about a position in Halmstad on Facebook.
Okay.
And I was looking for an academic job. I was actually a research associate professor at the time, but I wanted to do more teaching. And I'm originally from Egypt, so I thought when I saw the ad that Sweden is closer to Egypt, so I can easily visit my family.
Yeah, it's very close to Egypt. So, okay, so you come from Egypt, and then you go to the US.
Yes.
Washington.
That's where I studied. I studied in...
The state, or was it DC?
I was working in DC, but I graduated from Rice University in Texas.
I see, okay. And as a girl, were you all into computing and?
Yes, I actually wanted to work at first when I was very young with robotics.
Okay.
So when I was young, they sent this Pathfinder robot to Mars.
Yeah.
And this was very inspiring to me. I really wanted to work with robotics in the space. But then when I studied engineering in Cairo first, I didn't have a good opportunity to study robotics. So I started working in hardware in general. So designing computers, which can be a part of a robot if you think of it.
Yeah.
And then I moved to the United States, where I did my PhD also in hardware design and computer architecture and security. And basically, I don't do robotics really anymore, but my circuits can go anywhere.
Yeah, I realize, and it's all about speed. I realize.
Yes, it's all.
So just to and computer architecture. That's the area.
The general area. Yes.
Yeah. So just what really makes the data flowing more higher speed? Is it new materials, or is it the way you compute, or
there are many ways to speed up the flow of your data within a computer in order to get results quickly. One way is to make the circuits from a different technology that runs very fast. But currently, we actually fabricate our computers from CMOS technology, and CMOS technology is not getting faster with time. Actually, in the past few years, the speed up in our circuits is around 4% only. But you want to do 10 times faster and 100 times faster. So typically now everybody's moving towards parallelism. So, for example, imagine that you are riding a car with a friend, and you are going to one city and he is going to the other city. If you are riding the same car, and then the driver will drive him first, and then you will arrive next. It will take you longer time because you only have one car.
That's the situation, actually.
Yes,
that's always like that.
But if you have two cars and now everyone takes his own car, you can go directly to your destination, but then you have to pay for the other car. So it depends on your budget. Do you want to pay for speed or not, right? So parallelism is exactly that. You can use multiple processors, which is basically what does the computation, and try to speed up things, or you can sacrifice the speed and use one core if you want. And sometimes it's useless. For example, if I am going to Lund and you are going to Malmö, then it doesn't make sense because it will I am on your way anyways, right? So taking two cars is not beneficial anyways because we have to pass by Lund on the way, right? So sometimes parallelism does not work. And, it depends on the problem that you are trying to solve.
Well, I got the picture, so it's very good. But but how much is it about new materials? Because you will find new materials to make the new kind of chips. And tell me,
so
how much is that the case?
There is a big race between different scientists working on different technologies to see what will be the dominating technology after CMOS. And this will not happen next year, for example, because we have lots of inertia. You know how when we pay lots of money to fabricate something, you don't want to stop doing this because you already invested lots of money on this technology. So there is an inertia maintaining the technology for a while. Plus, we didn't really find the most mature technology to replace the current technology. But there are lots of candidate technologies. One of them is actually photonics, which is what I mentioned in my presentation about using optics and light to do the computation. So computation...
And that will be much higher speed then? Much
higher speed, but the technology has issues because, first of all, it's very difficult to have a memory in photonics. So you always need some electrical circuits with it. And if you put electrical circuits, then you slow down the system because the electrical circuit will be slower than the photonic circuit. So the other thing is that
now I'm still in the car. I'm waiting for a slower friend.
Yes,
Yeah.
exactly,
Yeah.
exactly.
I got
Yes, thank you.
Yeah.
And basically also another issue is that photonic circuits tend to be big, much bigger than the CMOS circuit. So you can imagine if I build you a whole processor from photonics, you probably will need a tractor to carry the phone for you. It will be very big. It can cover.
And that won't happen.
It's shrinking with time.
Yeah.
It's shrinking with time, so the technology is not mature enough yet.
Yeah. So where, in this research, where does this happen? All over the world?
All over the world. There are research groups everywhere. When I was working in George Washington University, there was a good, actually, photonics group doing research. It's very expensive to do photonics research because you need special equipment to do the experiments, which are very, very expensive.
And it's not certain that this will be the...
It's not certain because there are other technologies also into consideration. For example, one might consider different magnetic structures. Also, some people are considering DNA computing, for example, so biology to the rescue. And of course, the big next thing is quantum computing.
Yeah. So the next breakthrough, as you see it, will be?
Quantum computing is actually something that people are working hard to do it, and there are different technologies to implement quantum computers. But people are thinking this should be the next big step. But currently, the main issue with quantum computing is the error rate. So it's a technology that is not very reliable yet. So you do the computation, but you will get the wrong answer many times. So until they make it more reliable, people will not be able to use it. But it's very dangerous because it's very powerful. So people always say the day we have a real fully fledged quantum computer, security of everything will be broken. Right?
Yeah, we'll see that. And if we had the quantum technology right now, how much of your presentation would be worthless then? Could you use it with quantum technology? Would it be the same?
Well, I would have to say some abstract level ideas can work, but most of the low-level details are useless for quantum technology. So and this is why I think every computer engineer, computer scientist should learn a little bit about quantum technology because it's a bit different. And if suddenly this is what computers are made from, we all need to understand it. But it's not, I don't see it happening in my career time.
Okay. So, but let's go back to your presentation. I'm thinking, when it comes to speed, let's make this faster. Where do you start? I think that's the problem. How do you find the weakest point?
So you need to study the program you want to run.
Yeah.
So it's not enough to think of the fastest possible processor that will run any program. We say that if you want to do everything, you will not do anything properly. You will do them, but you will not do them in a perfect way. So you need to look at your software and extract the problems from the software. So your software can guide you.
So you extract that and you find, here's the crappy parts of this.
Yes.
That must be better. But so you have a list.
Yes.
And then
you start thinking, can we modify the architecture, the computer architecture, and add
you know
extra
that you can see that architecture.
Yes, definitely, and add extra circuits that will speed up this crappy part, as you say. Yeah. And
that's my language. I know better words.
No, I like crappy.
The crappy. Okay, great. So we have the crappy part. Let's get rid of them, and then you're thinking, or what are you doing?
So actually, currently, we have what we call high-level synthesis tools. And these are tools that can take a program, a software program, and convert it into a hardware circuit.
Okay.
And of course, the quality of the hardware circuit will be different depending on the program you are converting. But this can guide you, or you can get someone who is really good at hardware design and do it. But for our tools, we always envision automation. So we want things to be done automatically for you. So we adopt techniques from high-level senses, basically.
And is anyone else doing this at the moment? Some other place?
Yes, definitely. Lots of researchers from universities all over the world are doing similar research.
Yeah. So and you post. Oh, today we did this, and then we had that result.
Yes.
What have you been doing?
And then they will come and say, "Oh, we did something even better. Look at this."
Okay. So that kind of collaboration.
Yes. Yes.
Because
of course.
that's one of the words I really we talk about the need for collaborations for finding the new solutions.
Yes, and not only collaborations with people who do the same thing, but collaborations with people who do different things.
Yeah.
For example, when I do the optical search engine, I cannot do it alone. I am not someone who works in photonics. Usually, those are physics people.
Yeah.
So
and we know how they are.
Yeah, well, very smart people. But basically, in George Washington University, we were collaborating with physics
Okay,
people.
great.
And you always want to collaborate with people also from other disciplines, because this opens areas that you can.
New way of thinking.
Yes.
And alternatives.
Yes,
I understand.
exactly.
So there are people who are, let's call Yusra in Halmstad. She can help us. And then
For example, if they think what I'm doing is useful and it's something
they all do.
Yeah, something that they are not doing. For example, if you discover a new material and you think, oh, this material can be very good for doing multiplication and addition, you can come and say, Yusra, we have this cool material that you can use to build very fast multipliers or adders. And I would look at this material and see how to integrate it within a computer system. And then we have this hybrid system of two different technologies.
When it comes to speed, how much is about hardware and how much is about software?
I cannot tell that in numbers. It depends.
Can you be, let's not focus on the hardware bit because we are very good at that. It must be a software solution. Or is that a way of thinking? Can you think like that?
Yes, it depends. So let's say you are someone who is changing what your system is doing frequently. Then you don't want to have a hardware solution, a pure hardware solution, because what guarantees flexibility in a system is software, not the hardware. So you need to have a degree of programmability in the hardware in order to be able to change your application. But let's say I am only doing this and I want to do it the best way I can, then the natural way to do it is to do it in hardware.
I see.
Typically, hardware will be faster than software. If you are doing the same thing in hardware or in software, the hardware will be faster than software, and it can be 10 times faster, 100 times faster.
But then if we found the hardware solution, it will be easy to make it better in the software, I believe. I mean, it's always...
you can have a cycle where the hardware feeds the software and the software feeds the hardware, in a sense that if you have certain hardware like the GPU, the graphics processing unit, you need to program it in a certain way, right? So if you write software to use this unit, then the software itself needs to use, for example, a language called CUDA, which will configure the hardware properly to run the applications you want. In this sense, the hardware is impacting also the software. However, the software can also impact the hardware in the sense that we can change the hardware so that it can run the program faster. For example, if we have an application that requires matrix multiplication, then if the hardware can do matrix multiplication quickly for us, it will be faster and better.
You mentioned 6G. So what will we need to develop to be able to get the 6G standard?
Yeah.
What are we lacking?
I am not a communications person, but I would tell you from the hardware point of view, we'll need much faster hardware. Because if you look at it, first of all, the jump from 4G to 5G, we can see 100 times speed up.
Yeah.
And you should expect the same speed up when you jump from 5G to 6G.
And we're not there.
We are not there yet. The other thing also is that starting 5G, we are now having networks with lots of devices, different devices of different types. So now you have devices that will construct a smart city for you, for example. And all those devices will have different speeds and different softwares running on them. You cannot force everybody to use the same software on their phones, for example. And in this case, you also need to figure out how to make everything on the hardware level compatible in the side of speed, at least. Yeah.
And okay, last question. Take 10 years from now. What will be the big difference? 10 years ahead. That will, of course, it's tricky. But what do you think?
I think.
Okay. Last question. What do you think will happen in 10 years?
Well, I think in 10 years, devices will be less observable. So you will not observe the devices we are using. They will be embedded in everything, and we will not be. So you might have in your clothes some device that may be controlling the temperature for you. You might have lots of sensors all over your body. For example, we started already to see that if you have a smartwatch, it has a few sensors measuring your heart rate and maybe your blood pressure or something.
So my T-shirt would tell me you have to go to the doctor.
Exactly, maybe. Yeah. So I think.
Good morning.
Devices, hardware devices, will be a natural part of us and our life.
And even one more question: where will Yusra be? Where will she be in 10 years?
Well, I cannot retire in 10 years, so I still have to be working somewhere. But I hope I will be a professor by then, and I will be doing much cooler research, maybe in a new technology. Yeah.
Well, the best of luck. It was very nice meeting you.
Thank you.
I think I understand it, much better now.
Okay, great.
Thank you so much.
You're welcome.
And thank you all for participating and watching. Yeah. Let's go to some other of our episodes here from ELLIIT and learn some more. Thank you so much. Yeah.